Good afternoon, everybody, on Wednesday, February the 1st, 2023. We're almost at 3 years worth of Zoom weekly presentations, and I'm particularly pleased to welcome Dr. Sheldon Williamson today. He's a professor at the Institute of Technology in Ottawa, and he holds an NSERC Canada Research Chair in Electrical Energy Storage Systems. And Sheldon, we're looking forward to hearing your talk. So please, it's over to you.
Thank you, John. Thank you very much, and it's a pleasure to be here to present this talk on Electrification 2.0. Current status and future trends. Nice to meet all of you. A big thank you goes out to the Canadian Association for the Club of Rome for having me here. And one of my colleagues actually at Ontario Tech, Dr. Peter Stoet, who is also a member of the association, initiated this. So I would like to thank Peter for that initiative. So on to the talk and the slides. That's my first slide. Again, I would like to acknowledge much of the research work being done under the Canada Research Chairs program. For those of you who don't know, that's a federal funding agency from the government of Canada at the federal level. It's an endowed chair position, and my chair is specifically on energy storage systems for transportation electrification. So most of the work that you will see today in this presentation will cover topics, some of the burning and hot topics on e-mobility and electrified transport. What's the block? Where are the roadblocks, and what needs to be solved, and what's the current status? And some of the research that is being done here at Ontario Tech University in Oshawa, Canada. So first and foremost, it's an honor to present the group, the actual research group of professors who are working on several topics related to electrification, starting with Dr. Talochan Sidhu, who was the former Dean of Engineering here at Ontario Tech. And his research, in fact, is coincidentally, apart from being Dean, his research also deals with smart grids, renewable energy systems, so on and so forth. Dr. Vijay Sood, who spent almost 35 years, I think 35 plus years at Hydro-Quebec in Montreal, has joined our faculty for over like 20 years now, since the inception of the school. And he's the department chair for electrical engineering, and his research focuses on microgrids and DC systems, high voltage DC systems. So he's a pioneer in that field, including power electronics. Dr. Walid Ibrahim, his area of research is in the fields of smart grid and control systems. Dr. Mohammed Youssef, who is an expert in electric powertrains and drive systems, electric motor drive systems. And then lastly, myself, and my focus, as you know, is on batteries, electric vehicle chargers, and transportation electrification and e-mobility in general. There's been a big uptick in graduate research students in the last decade of the school's existence. Just between the 5 of us, we have over 150 graduate research students. So there's a big task force in research and electrification, specifically for automotive and electrification areas here at Ontario Tech. Those of you who know Ontario Tech, of Ontario Tech at Oshawa, know that we are an automotive-centric school. And so most of our trained engineers who come out of Ontario Tech, or formerly known as UOIT, are well-trained engineers in this field. We do have, between the 5 of us professors in electrification, in the electrification field, over 5,000 square meters of research lab space and 12 full-time lab technicians. Some of the thematic current research thrust areas of the group, of the Smart Transportation Electrification and Energy Research Group, we call ourselves the STEER group, is microgrids. One of them is microgrids, batteries and electric energy storage systems, and renewable energy system integration, such as solar, wind power, hydrogen, etc. We do look at transportation holistically and also at the micro level, from buses to bikes to scooters to two-wheelers to airplanes to sea and undersea vehicles as well, not just road vehicles, and the greenification of those vehicles. And finally, propulsion system, electric machines, electric propulsion systems, and motor drives areas. So pretty much a broad scope of what our research thrust areas are. So why electric transportation, right? I mean, and we've seen this many times now, and we know for the last decade or so, Canada has been one of the prime leaders of the world in terms of promoting electrified transportation. For one, it's the greenhouse gas emissions by the transportation sector. As you can see, almost quarter of the pie is taken up by vehicles that emit carbon monoxide and carbon dioxide. And this is taken directly from the Canadian Environmental Sustainability Indicators. It's an online document that you can also refer to, and I have shared that link right here as a reference right at the bottom. The other major contributor is oil and gas. And so obviously to fuel these vehicles, we do need oil and gas, right? And so that's another quarter of the pie taken up by the oil and gas industry. So as almost half of the industry, or half of the carbon monoxide or carbon dioxide emissions are contributed to by transportation and the oil and gas sector, right? And so the other interesting part of this pie is the electricity sector or the energy sector. It's almost 11% of the pie. And this is as of 2021, just from a couple of years back, almost a year back, in fact, is that electricity mix plays a vital role in electric transportation. How are we fueling electric vehicles, right? And this question comes up all the time. From time to time, okay, cars are green, battery electric cars are green, or hydrogen fuel cell cars are green. How are you going to fuel them? How are you going to generate the electricity, or how are you going to generate the hydrogen? So it's very, very important to find out how much does the electricity sector emit in our as part of greenhouse gas emissions. As you can see here, it's about 11%, which is not trivial by any stretch of imagination. This is quite a bit, right? So 11% accounts for is accounted for by electricity alone. So if these can be changed to renewables or green power, now green power could be solar and wind, and other natural sources, then yes, if that is going to be the electricity generation mix, then Canada can make a large claim in the electrification field in the world and make a big impact. So that's very important. That's why I threw it in this chart. And I think it's important to highlight that in terms of the carbon dioxide emissions. The energy use also. Okay, so you generate energy. Now, who uses them? This is from Natural Resources Canada, from their Energy Fact book, as I have referred to at the bottom here of this slide. This data is taken from that document. And as you can see here, almost 30% of the energy usage is by the transportation sector. And I say transportation because that includes heavy trucks, municipal vehicles, not just cars on the road, but also aircrafts and ships and marine vehicles, etc. Right? The rest of it is industrial, attributed to about 40% is attributed to industrial applications. And the rest is residential, agriculture, commercial, and institutional sectors. So again, transportation and other industrial transport means contribute quite a bit to the energy usage sector. Another big incentive is, we all know that by 2040, at least, or 2030, 35 and above, and over, we need to have almost all of our fleet, or at least half of the fleet, electrified. And that's the yellow plot. That's the trend of the yellow plot that you can see here, is that we need to go to all electric cars or some form of electrified vehicles by 2030 and beyond. And these are millions of cars per year on the y-axis, versus the years on the x-axis. As you can see here, we are right now around this 3% or 4% mark, where Canada's vehicles are electrified. This comes from this blog from bnf.com. There's a blog on electric vehicles and the new car sales. And this is real data that has been collected by that group. So I thought I'd share this slide as an incentive as to, hey, as you can see, the purple plots, the bars, increasing as we near 2035 and 2040, where we are looking at about half the fleet of vehicles sold in Canada to be electric, or some form of electric, like a hybrid electric or an electric. So that's very interesting. And the industry is working towards that. And some of our industry partners, at least here at Ontario Tech, we partner with GM, we partner with Ford, with Stellantis. Many of our students work at these companies and industry partners all around, in and around the automotive sector. So we really know that this is really happening. There's a push within to go towards sales in electric vehicles. So that's a big, big incentive. However, having said all of those good things, that's great, but there are these key challenges that still exist. First of all, is the limited range. Although there may be people who now claim that your electric vehicle can go 1,000 kilometers and above, but I've never seen it on the road. Okay, so this is in theory. They talk about theory, but in practice, really, there's a between 100 to 500 kilometer range limit. And this range doesn't stay constant. Let me tell you, the time you buy your car to another couple years and another couple years usage, you will see this range dwindling. You will reduce range by 50 or even 100 kilometers over, let's say, a period of 5 years, half the car's lifetime. So up to 10 years, if let's say you keep a car for 10 years, you might end up starting with 500 kilometers, but you may end up with 300 kilometer range, right? So you may have lost about 200 kilometers range because the battery capacity fades. So the battery cannot hold the charge as it was when it was new, right? And so that's the limitation. So limited range is a big, big practical limit, and that's why it's number one on my list here. Long charging times, that's definitely a big negative, which is 4 to 8 hours of charging time. It's very popular. Some of you who own electric cars know what I'm talking about. Limited charging infrastructure. And this is big because I know the Canadian government has been taking a big stand in increasing this and having charging infrastructure made more available to us. Now, here's the thing. If charging infrastructure becomes more available, let's say every, 50 kilometers, right? And every en route on the 401. Let's say we are driving around the 401 corridor. Let's say I'm going to Windsor. Okay, so I mean, if there are every 50 kilometers, I have a charging station where I can charge up in 5-10 minutes, that would do it. We could reduce the sizes of the batteries. We don't need that many batteries now. I mean, because in the back of your head, there's no range anxiety. The charging infrastructure is available, right? So availability of charging infrastructure right now is not the case, but I think in the next 5 to 10 years, we'll see every 50 kilometers or so, we should have charging stations in place, fast charging stations too, which are coming up very, very fast. Limited battery cycle life, I already talked about this. This is a big disadvantage, and that kind of ties in with the charging times, the charging infrastructure, the limited range, etc. So up to 1,000 cycles of good performance from a battery is what we get. It's not, these are lithium batteries, obviously. The other thing is also building lithium batteries. At the end of the day, we're dependent on lithium batteries. We're trying to look at alternative battery chemistries, but lithium is the go-to right now, go-to chemistry, which obviously leads to a lot of cost because lithium is not what we produce. Or even if we do, it's very limited. So we have to depend on the countries from the Far East to import lithium in order to manufacture them in Canada. So that's not really something sustainable or a model that is sustainable for jobs. moving forward, and for the economy in general. So safety issues and high initial costs are big players in terms of challenges as well, right? So that's my little short list. There can be several, and I'm open for discussion to this at the end of the talk. So where are we focusing now on in terms of R&D, right? So research and development, and I'm not talking just research and scientific research here. This is actual product development with the industry. We, the school, Ontario Tech in general, has this philosophy of not just keeping research in the pipeline and incubated, but also sharing this knowledge and transferring it to the industry. So almost, I would say 100% of my projects at least, and of my colleagues even in the group, is industry driven. So industry comes with these problems to us and we say, hey, we have a solution for you. We can do this for you. And they hire our students. And so there's this pipeline of hiring in the industry and making an impact on industrial products. So the focus areas within the group: EV charging, battery energy management, battery systems, energy storage systems in general, and electric drives for EVs. Yes, we are connected to the grid and we are connected to the electric machine, but the crux of the research and development work happens in the middle, right? The connectivity with the grid and then the actual energy usage on board the vehicle, so and everything in between. So that's something that was of prime importance past decade or so that I've been hired here to do this job, and integrating almost all our faculty members to focus in on these areas. So EV charging methods can be several. There are wired chargers, as you know, which are popular now. And then there's the up and coming wireless chargers or autonomous charging systems. Wired chargers can either be on board the vehicle or off board the vehicle. So on board the vehicle usually is called slow charging, where those are the current models. Electric vehicles that you buy now can have onboard chargers on the vehicle. They are less than 20 kilowatts in rating, peak power rating. You can go on board because the size gets really large after 20 kilowatts. That is the power density, what we say, power per kilogram. So it's a very slow charger. Off-board solutions are gaining a lot of interest. That is DC charging, that is direct DC contact with the battery. So those chargers are off-board. All the power electronics and the charger circuitry controls go off-board. So they'll sit inside the charging infrastructure and you can charge your vehicle with DC, direct DC. So that's usually rated greater than 20 kilowatts, and those can be fast, like fast as in within 5 to 10 minutes of charging. That's what we're looking at. At UOIT or at Ontario Tech, we ourselves have a 350 kilowatt fast charger system that we test. We have a living lab situation where we can test and collect real data from a 350 kilowatt charger. So imagine a 350 kilowatt charger can charge a Tesla, let's say a Model S, in like 5 minutes from 0 to 100%. That's outstanding, right? And that's something that we are looking at very seriously. Then there's the up and coming wireless chargers, where you can have inductive charging and capacitive charging. Inductive is electromagnetic based. So you look at magnetic induction and magnetic resonance. And capacitive charging is electrostatic based charging. And I'll talk a little bit about these in the ensuing slides. So ultra fast charging, right? So next to 10 minutes, let's say, these can be applied to chemistry such as lithium ion, nickel cadmium, or nickel metal hydride batteries. And the charge rates can range from anywhere from 1 C rate, that is at the rated current, to 10 times the rated current of a battery pack, right? So let's say you have a 100 amp battery, which is rated for 100 amps. You can charge it in 1 hour if you pass 100 amps, or you can charge it in 10 minutes if you're passing 10,000 amps, right? So 10 times. So those kind of things, or in 1 minute if you pass 10,000 amps or 10 kilo amps. Again, depends on the charger, depends on the battery chemistry, if it can take that current as well. Okay, so mind you, that's a debatable topic too. So you want your car to charge within 5 minutes, great, but can your battery take it? So those are some solutions we've also built around battery management systems. So DC fast charging systems, as I said, it's up and coming. The Society of Automotive Engineers have standards in place already. So as you can see, DC level 1, 2, and 3 standards, up to 400 amps DC at 250 kilowatts, right? So what we have on campus here is a 90 kilowatt plus a 250 kilowatt combination to give us a nominal charging power level of 350 kilowatt, near about 350 kilowatts at 600 amps, right? So one of my students built a 25 kilowatt DC fast charger, and this is some of the work we've done. Just so you know, Dr. Janmejaya Chanegowda graduated in 2020, and he built a novel DC fast charger. This was his experimental setup. As you can see here, this was the power converter. Our area is power electronics, and there's a lot of power electronics, as you can see in the circuitry here, connected with a 3-phase medium voltage grid line. We do have a grid simulator in the lab, and we have DC electronics loads in our labs, so we can emulate the charging algorithm that we would like to use, and the grid connectivity. Mind you, these chargers are bidirectional as well. So if you were to charge the vehicle, and if the vehicle has enough charge, it can also power the grid. So we call that vehicle to grid, bidirectional power flow. Well, you can go vehicle to home, you can go vehicle to grid, or you can go vehicle to anything. We call it V2X, right? So some of that work has been now transformed with a company whom I cannot name due to confidentiality issues into a product. So we've taken to a commercialization stage, now is at a TRL level 7 and above, and into production and testing and standardization right now. That's the power converter that went into the charger. So that's the actual view of the charger that we built for 25 kilowatts. And it'll go into a charger such as this, right, on the left-hand side, as you can see this picture here, into an actual DC fast charger. So that was some cool work that we are very proud of. We have a US patent pending for the control and the architecture of the power electronics, obviously. Then we did some work on a universal 6.5, well, this is a standard 6.6 kilowatt onboard battery charger. Now here's the motivation. There's a lot of there are a lot of chargers in the market. Right now, all the EVs that you have onboard chargers, but their plugs are different. Their input voltages are different. If you were in Europe or Asia, you would look at a 230 volt system, whereas single phase. Whereas if you were in North America, you would see a typical 110 volt single phase system, right? 60 hertz. Whereas Europe or Asia is more 50 hertz. Those of you who traveled around know it's a pain in the butt carrying with you the converter, right? We do this all the time for our laptops or whatever, phone chargers now. So the same story with the EVs. I mean, the standard chargers are different worldwide. What we've attempted here is to make the charger universal in input. So here you go. So you have the AC input from 85 to 265 volts RMS voltage. And the other beautiful thing about this product is the DC to DC converter output voltage is variable now, anywhere from 50 to 1000 volts DC. So if the battery voltages now go from the standard 300 or 400 volts all the way to 1000 volts, which is being proposed in the auto industry now, is high voltage DC, then our charger is capable of doing that. We, in fact, just got granted a patent. So this is the product. You can see this product right here is the OBC, or what we call the onboard charger. It's rated at 6.6 kilowatts. It's a level 2 charger. You can install it at home. It's portable, so you can take it anywhere in the world and charge your EV. So obviously the headache is the universal, is the chargers around the world are all different types, as you can see in the inset picture here. What we've done is made it universal and have one input and one standard output for different battery voltages, and still on board the vehicle, right? So it's really, really cool. Here you can see the US patent just granted as of last year, just before Christmas last year, December 6th, 2022. There's some ongoing work, more ongoing work on chargers, and now looking at fleets of vehicles being charged through this through this technology. Some more onboard chargers that we've built. We're looking at DC charging, so a lot of DC to DC converters, charging multiple outputs and fleets of vehicles from a common DC line or a DC microgrid, so to speak. This picture here shows several of these DC-DC converters and multiple outputs for EVs that can charge from the DC bus, just like this architecture over here. So a lot of work ongoing, and again, it's all attributed to the smart graduate PhD students and master students, as well as undergrad students here at Ontario Tech, who are doing some really cutting edge work. The other really nice part of this work is more recently, or at least last decade or so, we've started to work on smart chargers. And smart chargers with working with solar charging are a real winner for the economy, because homes have solar power anyway. Right now, many homes are converting to solar. So you can just say, let's say you put a 10 kilowatt solar panel on your home. Some of you may already have it. And I would love to discuss this at the end. And I'll open up when I open up the floor for questions and discussions. But we started to look at power electronic solutions to integrate EVs. Now, the problem though with solar and the grid and the EV is that there's a lot of power conversion going on. It's like, I mean, you have solar to convert to the AC, and then the grid is integrated in the home. There's the inverter, etc. So there's a lot of work going on there, a lot of power exchange going on, and which loses a lot of efficiency. So we've increased the efficiencies of the power in electronics and made this into a single stage smart charger inverter. So it can work as a charger and an inverter at the same time. So you can connect your solar to the EV. You can connect your solar to a battery energy storage, maybe at home for a UPS application, or you can connect your solar to the grid through the inverter, right? All in one box. So you can include your V2G, of course, it's bi-directional, so your vehicle can can send power back to the grid through the smart EV charger. You can send power back to the home through the smart EV charger, and you can send power back to anything. Let's say you're charging your laptop, V2X. So I call that V2X. Right? So that's a little animation, two animations that I'm showing you here. One through a home solar power that's charging your EV, or this could be even extended to commercial charging stations, like instead of gas stations, imagine a charging station now with solar panels on the roof, as you can see on the diagram or the picture on the right-hand side, where you have stationary energy storage, large energy storage on site, and that can actually provide DC charging to the DC chargers to charge the electric vehicles that come in. So you can have fast charging, solar panels, charging the stationary energy storage, connected to the grid, no doubt, which also has bidirectional power flow between the stationary storage and the grid. So there's all the power flows going on here, where our power converter can actually sit in. So Siddhartha, one of the past students, PhD students, actually built the conversion system for this. And we had a prototype that was going for that. There's your prototype for a 5 kilowatt inverter for DC fast charging, charger inverter for DC fast charging. This was an experimental setup in the lab. As you can see, we had the grid simulator, or the battery simulator, the grid simulator, which has bidirectional power, and the solar emulator. Sandra did some very good work along these lines as well. So she took the charger that we built and said, hey, I mean, solar is great, but what happens if on a snowy day, during winter, let's face it, we're in Canada up here, hey, there's 3 months, at least good 3 months of average snow on our solar panels, depending on location. What happens then? Can you charge your EVs green? No, I mean, you're dependent on the grid. So what about a system or an active snow removal system in place? You know, not going with brushes on top of the panels. I'm not talking about those. That's really bad. Actively melting snow through the power converter, which does the V2G and the charging. Can we have a bidirectional system that goes back into the panels and heats the diode so you can melt the snow? Okay, So that's what we did with Sandra's work, and we worked with an industry partner for that. This is, as you can see, we tested different panel types. In the bottom right-hand corner, you can see we created snow in the Automotive Center of Excellence up here at UOIT, which is we have the capability to do that within minutes. Those of you who've been there and have visited know the capabilities of ACE, the Automotive Center of Excellence. And that's the melting happening. After a couple hours of using our algorithm and the power electronics, we can see that there's melting happening of the snow. You can see patches now melting. And the temperatures were -40 degrees, maintained at -40 inside the chamber, environmental test chamber. So two strategies here. Here's our bidirectional DC-DC converter that we've been proposing. One is grid connected, and the other one is off-grid, as you can see. So we went with an off-grid option. And as you can see, the results are outstanding. We could get almost 80 to 90% snow removal within 2 hours of time, right? And so we can maintain charging and solar power even under snow conditions and heavy snow conditions. So there were thick layers of snow, as you can see here, right? So we generated that and then melted it through the DC-DC converter and smart control algorithms. Sandra did some good work. In fact, she got her master's last year and she's working in the industry now. She originally came to us from Colombia. Then we started focusing a lot on wireless charging. So there's a lot of wireless charging work ongoing in our group where we are creating these magnetic fields to interface with the charger on board through a wireless charging unit. Thereby, we can increase the drive range, battery volume reduction, because now you don't need as many batteries. The opportunity is there. You can charge anywhere where the opportunity presents itself. So you don't need as large a battery pack. Now, you can reduce the battery pack. Remember, as I said, as we increase the infrastructure or improve the infrastructure of charging, we don't really need as large a battery pack. So battery volume reduction is a big advantage of wireless charging. Battery lifespan increase because of that. Smaller batteries, larger lifespan. It's a convenience, so you don't have to ever think of charging because the charge is already happening. Charging is already happening wirelessly or autonomously. That's what they call quote unquote autonomous. And it's weatherproof. Most important, wired chargers are susceptible to humidity, dust, etc. Whereas wireless power chargers do not have that problem. Right, so it's a magnetic field, and magnetic fields, as you and I know, those who are hardcore electrical engineers or even material scientists would know that, hey, a magnetic field doesn't get affected by these external factors. And so you can maintain the efficiency of charging. You could either have static charging like this, where you have the charger underground, most of the charging system underground, the coils, the magnetic coil, a transmitter, and a receiver. It's almost like it is a transformer. At the end of the day, there's no core. You have a secondary winding, you have a primary, but there's air, right? It's air core. And so that's called static wireless charging, and there are standards in place for that. There are 4 levels of charging. You could even have in motion charging. You can pick up the charge while you go, right? So let's say we're in line for a coffee, in a drive-through, or in line for a drive-through for a burger. I don't know. Could be anything. And you're waiting to, it takes early mornings. Usually when I get my coffee, it's like at least 5-6 minutes entering the drive-through and getting out. Well, in 7 minutes, I can charge my battery pack to almost half using wireless charging. So let's say the drive-through was magnetically induced and the chargers are available. I can drive over these coils and pick up charge while I go and wait in line for my food to be served. And so in motion charging will come. I think it's up and coming technology as well. And we've been working on these areas since the last decade now. The other cool thing is in the future, this is may seem far-flung right now, but we can actually charge vehicles from each other as a fleet of electric vehicles. Let's say we're parked at a mall, so they can all charge each other. Or while driving, you can share power with other vehicles and transact energy. through wireless charging technology. So vehicle to vehicle, completely autonomous charging. So again, as drivers are taken out of the vehicle and the vehicles themselves are becoming driverless, we can go for autonomous or e-autonomous electrification or charging of these vehicles. Obviously, wireless charging ain't new. It's more than 100 years old. As you know, Nikola Tesla already proved that this could work in the late 1800s, early 1900s. In fact, he had the patent in 1900 on wireless power transfer, as you know. So, and of course, there's been products such as toothbrushes and implants, medical implants, and so on and so forth, using inductive power transfer technology. So again, there's also documentaries about this in the media now that, based off of Nikola Tesla's derivation or innovation of power transfer using inductive power. Then now we are looking at buses, charging from IPT, inductive power transfer, looking at forklifts, industrial mobility devices, and of course you can stretch your imagination to scooters and mobility devices that help people move around and so on and so forth. There are companies now that are popping up, Qualcomm being one of the big ones, Siemens, Bombardier, Whitericity down in the south of the border. We work a lot with Whitericity ourselves, Conductix, Evatrans, so on and so forth. So there are a few companies, obviously, that are in the market for these products now. And of course, we've started looking at EVs coming with charging pads, and Apple has started one for the iPhone. Those of you who are Apple iPhone owners, of the latest Apple iPhones has this charging pad, comes with it. You can charge your phone with it. So yeah, EVs are getting there as well from wireless charging standpoint. Level 1 by the Society of Automotive Engineers J2954 standard is at 3.5 kilowatts, and up to 22 kilowatts signifies wireless power transfer level 4 charging. And typically the switching frequencies of these inverters, high frequency inverters, is around 85 kilohertz. Dr. Kunwar Aditya, who got his PhD back in 2016, was one of the first pioneers of wireless power transfer technology design in our lab here at Ontario Tech. And he designed a 3.7 kilowatt system, and the efficiencies he got were close to 92% from a DC input to the DC output to the battery terminals. So at the input of the inverter, all the way to the output where the battery is charged. And you can see the coils that were designed by him in our lab right there. Wamshi went on to work for Tesla and now works for a company called Zoox, which makes EV charging infrastructure across the United States. He's a top-level manager now. He's also down south of the border, works in California, finished his master's at Ontario Tech and developed a 1 kilowatt charger for a golf cart, as you can see here. Yun Sang works with AMD right now, makes chips, power electronic chips, right here in Toronto. And he actually reduced the power conversion stages. His research was around power conversion stage reduction so that you can realize more efficient wireless power transfer. And his research led to efficiency increase of about 5 to 6%. So he got close to 96% efficiency from input DC to the battery. And that was breakthrough and groundbreaking, in fact. Deepak worked on capacitive power transfer. As you can see, capacitive plates are different from inductive coils. Capacitive plates discharge air between them, and therefore the transfer takes place through electrostatic discharge, just like any capacitor would do. So we create a capacitance, and typically these are aluminum plates, if you will, with air in between them. Now, you could have different dielectrics. You can play around if you're a material scientist and you fancy, I don't know, ceramic. You throw in ceramic in there and discharge power through it, you could get a higher power transfer. So there's the work being done now, not just in our lab, but worldwide. There are a lot of researchers now looking at capacitive power transfer, where you can eliminate some of the losses and efficiency downfalls of inductive power transfer. And so capacitive can gain more efficiency and give you more efficiency. We can look at hybrids too. We are looking at hybrids ourselves between inductive and capacitive power transfer with our industry partners. and looking at power levels of 22 kilowatts and above, so you can have fast charging using wireless power transfer. So Deepak did some good work. That was his work. Deepa Vincent, a recent PhD student as well as of last year, developed a hybrid concept. As I said, she did inductive and capacitive power transfer, and we built an 11 kilowatt level 3 charger in our lab. Some ongoing work with batteries, start to focus on batteries for the next 15 minutes here or so, is some issues with batteries, because the industry came to us and said, hey, batteries have been burning, overcharging, lifetime, all that kind of stuff needs to be eliminated. So cost. So we've seen Teslas catch fire, as you can see in this picture here, and Apple phones catching fire, and in recent Boeing aircrafts catching fire with lithium batteries. And so that actually happens to happen because of the capacity fade. And if you're charging these batteries fast, we don't know that you're killing the battery, but the battery inside is facing the issues, heating up. So the temperatures heat up, the capacity fades to hold charge. You keep charging at 100 plus amps. Unfortunately, the battery is going to give way sometime. So we need to monitor these. And for monitoring that, so David Capano, who was a master's student, designed a smart active cell balancing board, right? And so that was very smart for battery management systems, and mainly kept the batteries healthy. At the same time, you could fast charge the system. So this is what he did. Basically, you look at a module of cells, make sure that they all are balanced in their capacities, so as to keep the whole pack healthy, the whole battery pack healthy while you charge and discharge. So he did some good work on fast discharging conditions. This was the prototype. In the past, we also had Pablo Cassani, who did some work. So of course, the board looks like this. You can build this board for, again, from a cost standpoint, if a battery costs $100, this board would cost you $2. So it's about 2% of the cost of the pack itself. But what this board can do is give you double the lifetime. So instead of saying to the battery warranty in an EV, let's say you sell an EV and you have the battery pack, you say, oh, well, the warranty is 8 years, and after which you need to replace the battery pack. Well, I can give you 20 years for the same cost, or a little over the cost. Let's say you add these boards and say, I'm going to give you 16 plus years, nearly 20 years of lifetime. Well, you would buy it. You would definitely buy it, and this prototype can be added on in the form of a design for the battery pack. So we've worked with battery companies, and they like it a lot. In fact, this technology is taken off. It's a big business case. We also have some spin-offs and startups right now that we're talking to investors who are very interested in this technology, because that's a big roadblock, and we're solving them with very minimal cost. So these are just based on microcontrollers, MOSFETs. You can see the circuit. You can see the circuit board rather. The inductors obviously take the most space because it's a DC to DC converter. The 5 battery cells are hard connected to the board. And finally, the communication port, which talks to the vehicle controller. So we've started to build more and more of these smart battery management systems. You can see we've reduced the battery size by almost 60%, extended the calendar life, as I said to you, nearly 200%, and within 5% of the battery pack cost. The board that you saw was only mere 2% of the battery pack cost. So depending on your battery size and what you want to do, we've started to look at different ranges of cost. And that's the battery management system that we've proposed. We've started to look at EV battery second life as well. So now another big trend is what happens to the batteries after they finish their lifetime on the EV. Well, the truth to be told is that they still have about 60 to 70% of their energy intact, but it can't be used on the EV because they do not have the characteristics or the voltage levels to behave a certain way for the propulsion system. So they extract those batteries and then they say, oh, well, we'll recycle them. Well, there's no efficient recycling method still in place. They're toxic, right? Lithium is really toxic. So we found ways to give them a second life, a third life, a fourth, or whatever. So I just say, EV battery second life and beyond. And as you can see, there's some work being done. We have some battery management systems and models in place where we can make good use of second life. And these are some prototypes in these pictures that you can see that we've started to build. Another cool thing we've been doing is battery management systems on board need a lot of wires with the batteries. We want to remove these wires. Some of the companies want to remove the wires and sensors like temperature, voltage, current, change in voltage. All these sensors need wire harnesses and wires. Well, we've removed all of them and created smart battery models and put them in the cloud. So now your BMS is sitting somewhere in a cloud and it's telling your battery what to do. So as you can see in this picture, that's the idea. The battery is sitting in a cloud, or the battery management system is sitting in a cloud, which is telling all these vehicles, multiple vehicles and their batteries what to do, because we have comprehensive models. Or this cloud basically means a computer somewhere, right? So your computer is sitting somewhere and you're telling all these vehicles what to do from a central server. Okay, so there's some new work being done. This is a lot of estimation and control systems work to accurately model the battery, its behavior under temperature conditions, so on and so forth. We're also looking at battery safety, fast charging while maintaining the temperature constant. This has never been done before, and we have a US patent pending for this work, looking at fast charging within a minute or two, but maintaining capacity of the cell at the same time. So some smart algorithms are in place for that. We also started working on our own race team. We have our own Formula Electric race team. For those of you who know, may know or may not, Ontario Tech finished second in last year's electric vehicles SAE electric race competition for the design, or smart design of the accumulator system. So the undergrad students, in accordance with grad students as consultants, work with in harmony together. I was the supervisor for the team along with several of my colleagues here at Ontario Tech, and we did a comprehensive testing at Ontario Tech's ACE facility and come up with some of these designs for the accumulator. You can see some of them here. As you can see, our own battery management system, our own cells put together, so on and so forth in modules and sitting on the chassis of the electric vehicle. We've been looking at supercapacitors as an option for electric transit buses. And that's another option. We've been designing our own, very own autonomous buses here at Ontario Tech. And this is some of the pictures of that. So supercapacitors to replace batteries on buses, because buses really have transient power. They need power, not so much energy, because there's very less cruising time for these vehicles. Trains are the same thing. So looking at supercapacitors, streetcars in Toronto, for example, could utilize supercaps, and we can get rid of all the ugly overhead lines in the city. We've looked at supercaps for electric mass transit. More recent project, as you can see in this picture here, some drive cycles that we've developed for start-stop applications, municipality vehicles. Now we've been talking to the regional municipalities as well, who've shown interest to electrify their fleet, looking at supercapacitors or ultra capacitors. Right. One of my students, Nabi Sidhu, who finished his master's in 2017, developed switching supercapacitors for hybrid energy storage. We've started to look at modular multi-level converters for high power traction. Dr. Deepak Ronanki. We work with a traction inverter company that builds power electronic converters for trains and e-buses as a market. And again, we can't take the names of those companies in the interest of confidentiality, but these are the power converters that go into that. So there's a lot of our lab that has been developed around high power converters, modular multi-level converters. Dr. Rishi Menon finished his PhD in 2020 and also developed multi-level converters for permanent magnet motors. Dr. Arvind Kadam finished his PhD just last year. We built a motor emulator. Right, so instead of having the actual dynamometer to test the power propulsion system, we built a machine emulator. So you don't even need rotational parts. This module now is, of course, in the market, again, with an industry partner whom we partnered. So this is now a black box, which can emulate the entire motor drive system, so to speak, without actually having the machine on a dyno with a generator and a motor. So as to save a lot of cost and time in testing. Some other ongoing projects, we're still working on some smart energy management system, looking at wireless power transfer systems. These are some existing students who are working on that. We're still developing our autonomous bus with supercapacitors, with fast charging and wireless charging. Looking at grid interface now with EVs, as well as solar power. Along with the grid, we have our own microgrid here on campus, as you know, at Ontario Tech. Those of you who visited probably know. We're looking at level 1 and level 2 DC fast charging system, looking at multitude of modular converters interfacing with the grid for level 3 charging. And as I mentioned, we have the 350 kilowatt charger now on campus. We're looking at e-drones, some drone companies who are interested in this work, especially on battery range extension and wireless charging of drones. So that's something we are very, very proud of. We've even completed a project for the Canadian Department of National Defense in accordance with the Government of Canada to improve the range of drones for military applications. Just a virtual tour of the Automotive Center of Excellence. Those people who have been here, obviously, it's a world-class facility. It's a $145 million facility where we can create snow, sleet, rain, wind, gusts. We can emulate storms, all levels, highest level of storms, the wind speeds and gusts, and ice and rain and snow all at the same time. So we really have this test facility in our backyard, which helps us, our research, take shape and bear fruition in the form of commercial products. So here's some pictures, of course, of you can see our own very own e-bus being tested, or electric vehicle being tested in snow conditions. And then earlier I showed you the chargers, EV chargers using solar panel tested. We have all the technicians on hand who help our graduate students develop some of the best work that we could ever imagine in automotive electrification and transportation electrification and mobility. The Right Honorable Prime Minister, Mr. Justin Trudeau, was at our lab. He's been here multiple times to test for autonomous buses and announce funding for autonomous vehicles and electrification. This was the most recent picture from a few years back. As I said, we do have our own microgrid. The leads were Panasonic, Hydro One, Oshawa Power, which is more local from the Durham region. So this is all on campus. You can see some of the equipment on campus. The blue box here is the battery pack, 500 kilowatt hour battery pack from Panasonic, mostly in kind. Siemens solar power panels, solar panels donated by Siemens. And it's all connected to the grid through the switchgear system. And as you can see, the transformer connected to the grid on campus. That's another exterior view, and that's the SCADA system, or one-line diagram of the SCADA system of Oshawa Power, which shows where we are. Oshawa Power, the Oshawa Ontario Tech microgrid being on the Oshawa Power microgrid right at the bottom. So that's on the SCADA system for Oshawa Power. So that's in general the research focus areas at the STEER group, the energy storage right at the center of it, the charger in the grid, feeding into the battery or the energy storage system, the energy storage feeding it back to the grid or moving it on to the electric drive. And the electric drive systems for high power propulsion and medium level power propulsion has been proven, as I showed you several projects there on the electric drives. So that's the end of my talk, and that's my last slide. A big thank you again to the Canadian Association for the Club of Rome and for having me. And I'll open the floor up for questions now. Thank you.
Well, thank you very much, Sheldon. We have a mess of, we have many questions. And what I'm going to do is recognize someone who didn't even ask a question on the chat, which is almost a rule here. I'm going to go to the producer, the chief cook and bottle washer of our Zoom talks, and he also runs our websites because he's got quite a few years of experience with these guys that run on batteries. So Art Hunter, over to you.
Okay, thank you. I guess, Sheldon, I just wanted to comment that I've owned a Tesla Model 3 for about 16 months now, and I have seen the range drop from 567 kilometers to about 544. It hasn't been really massive drop, mind you. I do all my charging at home at 1 kilowatt. But I have used the Tesla fast charging, which go up to 250 kilowatts, and that will, of course, charge my long range battery from about 20% to 80% in somewhere between 20 and 35 minutes, just long enough to go and get a cup of coffee and walk the dog. Anyway, the other point is that I believe the lifetime that Tesla gives is 3,500 cycles, and over a 10-year period. And your comment on battery safety are correct. And there's been, as you know, a lot of work has gone on to prevent dendrite growth and what have you, and if you do proper battery management, you should not have a problem. And I'm always taken by the comment which I heard on the radio recently that said that internal combustion engine vehicles have burst into flame in Ontario at the rate of 10,000 a year, and I'm saying, wow, that's a big number. So I'm just want people to, put this in perspective. Now, one of the other things you talked about was the battery chemistry. Of course, that's very, very important. And the 4680 battery, I'm sure you're aware of, and they refer to that as the million-mile battery.
Yes.
It means you can charge it enough times for the vehicle to go 1,000,000 miles. It means you almost have to pass that down to your through subsequent generations to get that many miles. The rest of the vehicle will fall apart, but the battery will still be functioning. Anyway, question to you. You talked about vehicle to grid, and of course, this is extremely interesting. And could you tell us when this is going to come in Ontario and the rest of Canada? Do you have any sense of that?
The issue, so it is already available. Some of the battery manufacturers who supply batteries. A good question. Thanks, Art. You really summarized pretty much all the issues, some of the roadblocks, and very well articulated from your own experience from owning a Tesla, as you said. V2G is coming. It's coming fast. Within the next 5 years, I would foresee some of the leading companies providing this with service with the vehicle. Now, having said that, what is V2G going to solve, or what is the purpose? What are the services that V2G is going to provide, right, is the question. Is it a UPS system? Is it just like a battery sitting at home where you have the solar battery system now, which can power your lights when the lights go, right? When the power goes or electricity goes, or you have an electricity cut. Great, that's one application. What about peak shaving for the grid? Can your EVs in a fleet format, and coming from a power systems background, I think you'll appreciate this, is, hey, you could have peak shaving as a service, okay? So now, all of this said and done, I just throw out two examples. There's several that we could think of, and we can chat on this offline in the interest of time, is battery life. Battery have limited cycles. The EV battery has very limited cycles. Okay, so now you're saying to me that you're going to send power to the grid. Yeah, you're going to make a couple dollars on it. It's a transactional thing. Great, but what if one of your family members is in an emergency? You need to go to the hospital, and you've discharged your battery into the grid. Now you don't have your card available to you to go. So now what we've been doing is looking at certain V2G concepts, not take the whole battery capacity and say, hey, everything's available for V2G. No. Let's say you have a 100 kilowatt hour battery, and let's say I dedicate 25 kilowatt hours to V2G. Which are the healthiest batteries that can do that? That's something circling back to the research that I presented. Smart BMS, identifying within the pack what modules of batteries are available for V2G. You see what I'm saying? So not all of it, and it is coming. We've been working with certain companies, and they're Ontario-based, I'll tell you that are building power converters that will interface with the battery and connect to the grid for V2G. But not all of the battery capacity will be used for the V2G. And you don't need that. Honestly, 25 kilowatts for an hour for a house is more than enough. For an average Canadian home is more than enough to power for several hours. In fact, I don't know, let's say 3 to 4 hours easily. With 25 kilowatt hours, you can easily do 3 to 4 hours of backup power for a home, for example. So those sort of services. And like I said, within the next 4 or 5 years, I see several auto companies who've already tried and tested this technology. It'll come in the market.
Okay.
So I hope I answered your question.
Yes, thank you.
Okay. Thanks, Art and Sheldon. Claude Butner, I apologize. I didn't advise you were on deck.
Actually,
you're
you
on
did.
now if you can join us. And following you is Richard van der Gat. So, Claude, please.
Yes, I actually have several questions, but I'm going to focus in the interest of time on one of them. You mentioned some very impressive numbers on the efficiency of the roadway, but you
wireless
also,
charging. Yep.
yes,
yep.
but you also answered in your talk on the vehicle efficiency, which is still impressive, that from the inverter to the battery. But I'm actually more concerned intuitively. I'm not an electrical engineer, but I'm the efficiency of the having the grid feed all of those coils on a roadway, whether or not there's a car there, that's got to have some parasitic loss that it would bring the whole system. So in other words, the vehicle is a component of that recharging system. So do you have a feeling of what it is today? And then also part of my question was, sometimes you can make some educated guesses as to where the physical limitations are and efficiency on such a system.
Yes. So Claude, thanks for that question. Definitely, if you're charging a fleet of vehicles, we could run into problems that there's an odd vehicle or two that has all these parasitics, as you mentioned. We've been looking at smart shielding techniques. So we've to shield out all of the parasitics from vehicles, electronics that it carries or whatnot, so that we can focus or zero in only on the efficient coil design. So we shield out the, let's say, for example, one would say interference, magnetic interference, EMI, or electromagnetic compatibility could be an issue. So those things we take and incorporate into our designs. We make sure that we design shielding methods so that we can shield out all this noise and only focus on the pure power transfer, so as to speak real power, right? So it's very, very important that the reactive components are shunned out, and we also make sure through resonance circuits that reactive power is kept at a minimum, so that we resonate the inductive part with capacitive, we cancel out the reactive part and make sure that real power is transferred so that we can keep the power factor as close as possible to 1. So from a power system standpoint, now even
Whoop, we lost your voice there.
Thank you. Richard, you're on.
Can you hear me now?
Yes.
Yep.
Sorry?
Yes.
Okay.
Can you hear me now? Yeah, sorry, I just cut out for a moment there. So to answer Claude, Claude, are you there?
I am, yes.
Yes, sorry about that. It's the issue with the wireless headphone. It just went out of range. Long answer short, yes, making sure through resonance circuits, through shielding circuits, making sure that the power transfer is real power from primary to secondary, albeit the vehicle is part of the power transfer system now, is we can cut out a lot of the parasitic losses. And we have proven that. And that's why the efficiencies are that high.
But what is the system as a whole currently? Because even though you're not focused on designing the in-road system, I suspect that's where the parasitic loss will take place.
Oh, you talk from the grid side?
No, yeah, from your powering the roadway, from the place where the power goes into the roadway system until it gets to the battery, what is the efficiency?
Oh, that is from the input here, exactly. From the roadway to there, the efficiency
No, from the grid that powers the roadways, because your vehicle is only a component of the recharging system. And I suspect that you're going to get some very disappointing numbers. It will take a lot of energy to power.
Input, yes. When I say input DC to the output battery DC terminal is including the roadway power converters unit. So the power system that falls under the road is from the input DC all the way to the coil, which is under the road. And then the vehicle has a coil, which is a pickup, the secondary side, and goes to the DC terminal of the battery. All of it included is 94.5%.
All right. So again, I will defer to your research, but that seems incredibly high.
Yes, absolutely. And in fact, there are companies now that are proposing close to or pushing for 97% and above, and making it compatible with wired chargers.
Folks, we have more than 20 people who've asked questions. My guess is that maybe 10 might sneak in before we shut this down. Richard, you are next, followed by William Reese.
Okay.
Off you go.
Thank you. I have a two-part question. One is the equalizer prototype ready for prime time? I loved your talk. It was great. And we're getting an Ionic 5 the 2023 in 2 weeks. So I thought, geez, you know, that equalizer prototype sounds really interesting. I'd love to have it in my new car. If you want to make us a prototype, we'd be happy to have one. You know,
definitely. Listen, there's a lot of work going on in this field. Batteries are something, battery management systems are something that is being looked at very seriously by battery companies and auto manufacturers right now. And equalizer prototypes from the passive technology moving towards the active technology with lower costs is something that is a real research problem. And so we've started to now almost come to a TRL level 6 where we can now commercialize and make it into a prototype.
Perfect. The second part of my question is, my understanding is that it's better not to charge to 100% and not to use superchargers. Is that right? To extend the life of your battery? Is that right?
Very right. Absolutely, Richard. It's health that is of prime importance of the battery. So charging them at super fast charging rates, such as the 250 kilowatt Tesla charger, let's say, for example, right? Great. Like you can get a 5-minute charge or a 10-minute charge, but it's not good to charge all the way to 100%. And there's a range within that power level, with a range within the battery state of charge, so to speak, where you can actually use all of this 250 kilowatts and the battery will stay healthy. But it's typically way lower than even 25 or 30 kilowatts that you're actually charging the battery at, so as to keep it healthy and intact, the cycle life intact.
So where do you, instead of charging to 100%, where do you charge it to?
Usually it's cut off at about 70-75%, after which from 75 to 90, the last 15-20% would be more slow charging or level 2 charging, not so much level 3 and above DC.
No. I think we'd be using level 2 anyway. I don't see us going.
Level 2 is about the optimal size right now for batteries. But like I said in a couple of my slides, you know, if the charging algorithms are redesigned, taking temperature into consideration, because what is the main factor that is affecting these battery, the health issue or the cycle life is temperature. Because of the fast charging, they say, okay, you can only charge for 20-30% of the entire range at very fast charging. then the rest of it is like below 25 kilowatts anyway, then what's the point? Well, why can't I use all of it to charge the whole thing in 5 minutes? The issue being the temperature of the cells, the modules, and the pack. And so some of those algorithms that we've been designing now is to feed back temperature in the control loop, keeping temperature under control within a permissible limit so that we can charge all of the modules within 5 minutes. So that's some cutting edge work as well.
Yeah.
Thank you.
Thank you.
Ralph Torrey, you're on deck following Bill Rees. Please, Bill, go ahead.
Okay, thank you. That was an extremely interesting presentation, Sheldon. I'm going to
Thank you, Bill.
Yeah, so 2 questions. I had a bunch, but you sort of answered a couple of them. At present, all the equipment you've been talking about, including EVs and all the charging, and is all made using fossil fuels. In fact, the grid's made and everything, from mining to manufacturing. So at what point can we anticipate that this entire system will be electrified and self-sufficient? In other words, we use the products of the system itself to produce itself, plus provide the extra energy needed to run society.
Yeah, but that's a very interesting question. And it's very philosophical. If you think about it, different people will have different answers for this as well. So my opinion, I don't know, it's just my opinion. Even if you look at renewables, again, the manufacture of solar cells, manufacturing of batteries is not yet sustainable, right? So I think it's really, really important to look at natural resources, how to transport them to the site where the energy is going to be used has to be made sustainable first. The actual raw material extraction to get it to the source, be it electricity grid or whatever, right? Hydrogen, same thing. People say, oh, fuel cells. Is it green? Well, there's gray, there's blue hydrogen, there's green hydrogen, there's black hydrogen, I don't know. Honestly, I don't have a real firm answer for you, but I really feel that we need to focus in or zero in on the sources. One really clean source, and we should be proud of in Canada, is water or hydro power, right? It's really renewable. But again, generating or using water in a smart way using micro turbines could be one way, but that's only the interim solution. Instead of using large turbines, which we've been doing, again, manufacture of turbine and its parts are not sustainable probably because they use a lot of energy. Same thing as you asked, but looking at micro turbines or smaller turbines may be the answer in the interim. So that would be my answer. And that's happening already. There are several plants, micro turbine plants in and around Quebec, Ontario, Northern Ontario especially. And so I think that therein lies the start of the solution, at least.
Thank you, Sheldon. I should have let you know that William Rees is an academic, an emeritus professor, but not in your discipline, in zoology, I think. And
okay.
But I think you're well on the way to becoming a generalist, and maybe you'll run for Parliament even one day. So Ralph Torrey, please, you're on, and following Ralph will be Peter Bukowski. Ralph?
Hi, Ralph.
Hi, Sheldon. I actually didn't have a question, John. I just wanted to say that how great the presentation was. We know that electrification of the transportation sector is pretty much universally regarded as a necessary component of the transition to a post-fossil fuel era. And what you've done is really given us a sense of where the rubber meets the road. If people are wincing at the use of that phrase probably right now, but where the rubber really meets the road in terms of the technical work that has to be done to make this happen and how fast it's proceeding. I mean, it's mind-blowing. When I first started doing energy scenarios, which is admittedly getting to be a while ago, but we didn't dare assume electric vehicles. We would have been laughed out of the room. And now here we see them being right at the center of both private and public sector strategies and policies for our energy future. So very exciting. And the other thing is, I get a sense listening to you of just how many moving parts there are in the area that you're working in. Not only it's complicated enough and moving quickly enough what's going on with the electrification of the vehicles themselves, but it all has to be done in a way that fits with other technologies and systems which are also undergoing rapid evolution, from batteries to home energy systems to the distribution systems that are employed by the grid itself. And it's really remarkable to hear directly from a practitioner, to see the way that you and your colleagues at your lab are making these contributions and contributing to what surely must be one of the most complicated and complex of the issues surrounding the transition to a low carbon future. So I guess I'm just saying thank you. I'm not going to ask any questions.
Well, thank you.
I'm just taking notes and learning.
Yes, thank you, Ralph. No, definitely. I mean, this is something that's not, this is just the beginning. It's just scratching the surface, if I may add. Although this is worth of my own experience of 25 plus years of research and development and working with industry, these are some still burning questions that are remaining to be answered. You know, there's a lot more to be done to make this a sustainable future, as I was just answering before this. So it's really something that, yeah, which drives us every day, brings us to work every day, and the passion to do that. So thank you for your comments, Ralph. Appreciate it.
Phil Riley, you're on deck, and I'd now like to turn to Peter Bukowski, who's on audio only, Sheldon. Peter?
Sure.
Hi, Sheldon. Peter Bukowski. I'm a fossil fuels, oil sands dinosaur of over 45 years experience now working in the field. Two questions, one related to ultimate taxation. Putting all these charging stations in, some have gone in with private money, most have required public subsidies. For the massive amount of charging stations, are we expecting another big tax hike and debt? The other question, you think that we can go to smaller batteries because range anxiety will not be an issue? Most of Canada is not Southern Ontario. I can see that you can drive across Canada in the winter, but I don't see most people covering most of Canada being able to do it without range anxiety if you've got a small battery.
Right. So, Peter, that's a good question. Either charging stations or wireless charging outlets, we need the infrastructure in place. So in order to reduce the size of the battery, we need the charging stations in place. Otherwise, you're going to only shift the cost from the building of the charging stations to actually paying for the battery cost on the car. The question being, either or, you're going to have to pay. My main concern is batteries on cars don't last more than 10 years. And so that means 3,000 cycles, as we were just talking to Art, in fact, saying, hey, you know, the battery range is already dwindling. He's had his car for what, 16 months, if I'm not mistaken, Art. And you've already seen like a nearly, I don't know, 30-kilometer range drop. So, yes. Sorry?
Yes, correct.
Right. So now who pays? Okay, let's say you run out of effective range and cycles, and now you have to resell your car. Who will buy this car from you? Who takes on the cost? So again, I'm not in a position to, I can solve problems on the battery, give you 20 years lifetime for a mere $2 per cell investment, but I am not probably the one to answer who's going to pay for the charge. So charging stations, once there are enough charging spots, all I know is it'll reduce the stress on the battery and the battery management system. So reducing the battery size will make it more efficient, give it more lifetime, so on and so forth. But in terms of, as you are very right, What happens, Peter, to who pays, again, tax dollars coming out of our own pockets, you and me, to build these charging stations? Definitely, I don't know how the model is going to work. I'm not in a position to answer that question. I'm one who can build an effective and a more efficient charger. Smaller chargers can do the job, probably less cost. I can do that. But who pays for it eventually? I'm not the one who can answer that. That is one for the utilities and one for the government. So, but thank you for your question. I hope I answered your question in bits and pieces from a technological standpoint.
What separation do you see as a requirement between charging stations? And I guess I'm thinking of a route like Highway 11 across Northern Ontario.
Yes. So with current battery sizes, we can go maybe 150, 200 kilometers, and with very efficient chargers, I would say that would be the ideal range, 150 to 200 kilometers before you start to get anxious. Intermediate chargers, like small chargers, like 25, 50 kilowatt chargers, you can still have those. They're not very costly. They can be owned by the service provider, let's say, I don't know, an en route, which is government owned at the end of the day, within Ontario at least, across the 401. But just as a example model. But yeah, I think the ideal range would be that 150, 200 kilometer range.
Thank you very much, Sheldon. Have a good day.
Welcome, Peter. You too. Thank you.
John Meyer, if you can put your video on very quickly, you made a related point. Off to you, John, about range in the winter crossing Canada. Unmute, please.
He is unmuted. He is unmuted. He's having a problem. He's not coming out.
Okay. In that case, let John just hold on a moment. We'll go to Phil Riley.
Okay, well, Sheldon, thank you very much for the presentation. I found it very interesting.
Welcome. Thank you, Phil.
I'm not an engineer, but I am a energy type of person in that 13 years ago, I installed a microfit system. And one of my questions has to do with it, but I also have questions about EVs. So about the microfit system. When the grid goes down, I lose the ability to both provide power to the grid and to consume power because there is a circuit that cuts it off both from my house and from the grid. So any power that is being generated is now lost. Now going to the EV chargers, I have had EVs for about 5 years at this point. I've just upgraded to a Kia Soul, which has a range in the neighborhood of about 350 kilometers.
Yes.
And as an example, I have a daughter that lives near Salina, so in the Oshawa area, which is 313 kilometers from where I am. So idealistically, I should be able to get from here to there without charging. But knowing that things can go amiss while en route, I choose to charge along the way. So for instance, going between Ottawa and Oshawa, there are very few charging stations.
Yes.
And so when you go into one of the charging stations and there's only one outlet, if you come to somebody who's already there, they have the right to continue, which means they may be there for 45 minutes to an hour before it's now your turn to sit there. Okay. And so then it comes back to who is going to take on the responsibility for inserting for the infrastructure for the number of cars that are using the highways, because as you travel from Ottawa to Toronto, you will very often have a dozen cars pass an intersection in 30 seconds. And the more that we have electric vehicles, all of those cars in a longer route are going to need to be pulled over.
Absolutely.
Where there may be food or a bathroom availability, and they're not there. So it's not just the
Yes.
charging facility, it's the other infrastructure that is required. And so then
Yes.
it goes back to, as you are doing your planning at almost pre-purchase of an EV, the amount of information that the auto industry is giving to the new consumer is pitiful. They don't
Yep.
tell you what your different cars have the capability of predicting en route, what your planning opportunities
Yes.
are, whether the chargers are occupied or inoperable or all of that. So it's
Yes.
just a hellhole of experience
Yes.
to drive an EV at this time. I
Yes.
honestly cannot say that I am promoting driving an EV if you want to have a peaceful life and a peaceful wife, because I'll tell my
No, definitely, Phil. Hey, listen, good point. And I have, like, we've started working with a company, a startup right now, and startups think of these things. Is the exact point that you brought up is, hey, like a couple people are already charging from the outlets, and where am I supposed to go? So if you have your own charger, like a portable charger, which can get you 50 or 100 kilometers of range, then that would be good. But listen, for that, you need a stationary battery storage system. You need a charging system of your own with a solar panel or connectivity to the grid at home. So you have this charged up battery pack that you're carrying with you now. The other scenario right now is I see a future for swapping batteries. And here's how it will work. Now the EVs that you and I buy, well, we say you and I, but not many people have EVs, but still the EVs that we have today have a large battery pack in it. You can't touch it. You have no access to it. And I'm sure you've read somewhere in probably reading or educating yourself that swappable batteries are being looked at in certain countries, in certain spaces, probably not yet in Canada, but we've started working with some startups. So portable chargers and looking at swappable battery modules. So let's say you have a case where you can go 20 modules, plug in, plug out. Just like it clicks in, clicks out with a handle. You increase your range that way. So you can add more batteries and go without hesitating. And you don't need to wait for charging for that. It's like a 10-second process. Remove one battery, throw it in the back in your trunk, put the other battery module in, and you're ready to go. While you go grab your coffee or whatever. So those are some solutions which are coming. I understand right now we really need infrastructure. Who's going to pay for it? Going back to Peter's question, it's like, okay, so now what? Who pays for all this infrastructure? It's a closed loop. It's a catch-22 situation. But we really do need, and the other one is wireless charging, as I said. So with one charging outlet, now you won't have the problem. You can power several coils under the charging spots. If you just place the coil, you have a wireless pickup coil on your car, you charge, and you don't need to think about whether or not there's a charging station outlet available. So those things are coming, but we have to wait another 3, 4, 5 years till we really see mass acceptance of these technologies.
So one of the other points that I have has to do with
Phil,
with the availability of non-proprietary charging stations, because at this point, paying for electricity depends on you having an account with some of the different chargers rather than just being able to have your MasterCard and pay and away you go.
Agreed. I agree with you, Phil. Thanks.
Thank you. Susha, has your question been answered? If not, please come on right away or after the next speaker, who is Ted Manning. So let's go to Ted with Susha on deck if he wishes to. And following that, we've got about 5-7 minutes left. I plan to go to Bill Reese. So off you go, Susha, if you're on.
Okay.
If not, Ted Manning. Oh, Susha, go.
Okay. Okay, thank you, Sheldon. Very good presentation.
Thank you, Susha.
And my question is, I was looking at Tesla Model 3
Mhm.
in the last few days for 2023. And the impression I got, it can go up to 450 kilometer range.
Yep.
And it can be, from the power specification I looked at, it can be charged in 20 minutes if it is 100% charged on a high powered booster. So my daughter is considering and looking at buying a Tesla. So I was interrogating for her. So from what I hear today, that we should not charge batteries for more than 80%.
Yeah, well, there's a cutoff already on the charger and on the battery system. It'll automatically cut off and reduce the charge level. Where you think that, okay, you have a 150 kilowatt charger, but the system will already taper the charge level automatically or modulate it to make sure that the battery is still healthy. So you don't have to worry about it. And it's a great choice. The Tesla Model 3 is a great choice. It has, as you said, 275-mile range, or about give or take 400 something kilometer range. So it's a great choice. It's a reasonable cost vehicle. And I think, you know, I don't know, Art, I think yours is an S, I think you said.
Yeah,
Yeah.
just let me answer that quickly.
Yes.
Susha, I charge up to 100% only when I'm going on a long trip. The rest of the time, I don't go above 80.
Okay, so if I'm going from Ottawa to Toronto, which is about 400 kilometers, and the range is 450, but in the winter time, I don't know in the winter time, like today, the temperature this week, how much derating it would have, for instance, from 450 to,
yes,
you know, it won't be 450.
Good question. Good question, Susha, and I think it's a valid question because in the cold temperatures, even while driving, your range won't be the same because you discharge rather quickly. The capacity fade of the batteries enhance the discharge rate, even though your performance is still the same as it was when it was a good ambient temperature of 30 degrees, whereas on a day like a negative 15 degrees Celsius day, the performance won't be affected, but your range will be affected because your batteries discharge faster. So the cost of the battery pack is directly proportional to the thermal management system. I can tell you that. Tesla uses a thermal management system as well on board, and those are the nitty-gritty integral details. But the cost will have to go up if they invest in better thermally managed systems. So that means to heat up the batteries in cold temperature conditions so as to have ambient temperature and give you the same range.
If I could just step in for
yes.
a second
Art,
here. The Tesla charging system does it all for you. You go on Navigator and it tells you where to stop. I've gone from here to Toronto, and after 3-4 hours, it says pull into Belleville, you pull in there, you charge up, and then you carry on.
Okay, thanks. Look, I'm going to try and squeeze 2 more people in before the recording ends. Ted Manning, have you got a quick point to make?
Yeah, I really like, Sheldon, your idea of building the infrastructure in so as you drive over it, it charges your car on the way or when you park it. But I want to come back to this. I've been in government long enough to know that you just don't make it happen. You got to figure out the technology that's going to allow them to collect money from you as you drive over it. How are people likely to be able to pay as they charge themselves when they drive through a parking lot or drive over a drive along?
Yes, definitely. It has to have IDs. The cars have to have IDs, and they're connected to that, right? And so you get a bill. Just like we go, I don't know if in Ontario we use the 407, for example, right? I mean, you get a bill at home, it identifies your number plate, your ID'd, and you get a bill. So
and will it be able to judge how much power you got as you went over each one of these things?
Yes, yeah,
I'm just asking you because I'm not a technologist and I desperately see a
yes,
need
no, this is definitely a valid
how
question.
This is going to work. Thanks.
Absolutely valid question, and it's an energy meter at the end of the day. How much energy have you used? charge your battery, and you owe a certain entity certain amount of dollars to do that, right? So
Thank you very much. Sounds like a good.
thank you, Ted.
Thank you. Sheldon, I'd just like to remind you that the membership of KCOR covers an enormous range of academic disciplines, from anthropology to zoology and most letters in between, and
Yes.
careers to match.
Yes.
Bill Rees,
Excellent.
our professor of ecology, probably captures that range as an ultimate generalist. So Bill Rees, over to you. Bill, where have you gone? All right, that's too bad. Let me just read
That's
to
okay.
you, if I may, Sheldon, what he wrote.
Yes.
Hesitate to raise this again, but we should not be excessively mesmerized by technological wizardry. The world is in general ecological overshoot, of which carbon dioxide emissions are only one symptom. Indeed, most environmental problems are results of previous techno advances. My real concern is that if all this tech actually works out, it would enable business as usual via alternative means, including continued material growth, massive increases in demand for everything, and I've lost my place. So that gives you enough of the flavor.
Absolutely,
So,
and I agree with it. Absolutely agree. Like there's no one sustainable pathway. Let's just put it that way.
Well, I'm going to invite Ted Manning to come on for a few final words. Ted, are you ready to do that?
It says I cannot start my video because the
Okay.
host stopped it. Has the host started it again? It says
All
the
right.
host has asked me, okay, takes two to tango. And this time we can actually see my picture. You couldn't before. I found this very interesting because as somebody who's driving a vehicle that's reaching the end of its gas days, I'm desperate to find something that's going to be a sustainable solution and affordable. And I can't start my video again because the host has stopped it, which is again interesting. Anyway, I will continue to speak and hopefully the video decides to come.
It's okay.
Back.
We can hear you just fine.
We can hear
Ted.
you. That's fine. Yep.
Very
yep.
good.
Go ahead, Ted.
But I'm on primarily to thank you for a very interesting presentation on behalf of the entire board and all of the other folks who belong to KCOR and who watch this. And we are also going to ask those of you who do not now belong to please belong. And we are delighted to have people make presentations to us that are intellectually stimulating, that are always worthy. And in fact, we are able now to share most of them directly with the International Club of Rome for those who are interested. We're getting quite a few watches, quite a few YouTube things. It's definitely worthwhile. You will see on the screen, those of you who can see it, I can see the screen, I just can't see me.
That's all right. We'll survive.
Yeah, that's okay. I exist. At least believe me, I exist. But we are delighted to have very stimulating, interesting, and productive contributions. And I will also note that every week there's something on, and we are now on our getting close to 300, 200, well over 200, I think, presentations. And when Art and I started this originally, we thought, let's try a couple and see if they work under COVID. And we had marvelous serendipity, and it really did work. So we are delighted you're still coming. We're delighted you're all still participating. And I will now ask Art to open it up and let everybody talk to each other as a general conversation, as we do at the end of every one of these. For anybody who has remaining questions and comments, please go ahead. Thank you.
Thank you, Ted. Thank you.